Hello and welcome to the AI Research Roundup. I am Alex, your host. Today is May 8th, 2025. We are looking at a research paper from Hugging Face's trending list, published 3 days ago, titled LLaMA-Omni2, LLM-based real-time spoken chatbot with autoregressive streaming speech synthesis. This paper introduces LLaMA-Omni2, a new series of speech-language models, or speech LMs. These are AI systems for understanding and generating spoken language. It aims for high-quality, real-time speech interaction using an autoregressive streaming speech decoder, which generates speech bit by bit for that real-time feel, outperforming older models with less training data. Alright, so this figure lays out LLaMA-Omni2's design, which is key to its performance. On the left, the architecture. Your speech enters a speech encoder, converting audio into data the AI processes, and a speech adapter, helping the main large language model understand. Its text response then hits a gate fusion module, smartly combining text and speech elements. Then, a text-to-speech language model plans the spoken output, and a vocoder crafts the sound waves. The right side shows their efficient two-stage training, optimizing parts step by step. Moving to the results. This table benchmarks LLaMA-Omni2 against other speech-language models. We see metrics like ASRWER, or automatic speech recognition, word error rate. This shows how well it transcribes speech, so lower scores are better. And UTMOS, or user-rated test mean opinion score, gauging speech naturalness, higher is better. The LLaMA-Omni2 models, particularly larger ones, demonstrate strong accuracy, low automatic speech recognition, word error rate, high user-rated test mean opinion score, and importantly, low response latency, often around 600 milliseconds, making them suitable for that real-time conversation we talked about, outperforming previous systems. Okay, this next table delves into what is called an ablation study, which is where the researchers test different parts of their system to see what works best. Specifically, they looked at various pre-training strategies for the text-to-speech component, or TTS, that is the part that generates the spoken voice. We see that streaming TTS yields the highest speech-to-speech quality score and the lowest automatic speech recognition, word error rate. This outcome, compared to training from scratch or just using text pre-trained methods, really shows the effectiveness of their chosen approach for generating that natural, real-time speech. Alright, building on those ablation studies, this table here looks at another crucial part for that real-time feel, their read/write strategy for streaming speech. The R and W values essentially control how many units of speech information the model reads from the input and writes as output in each processing step. We can see a trade-off. Smaller values for R and W, like 1 and 5, give the lowest latency, just over 450 milliseconds. But increasing these values slightly, for example to R equals 3 and W equals 10, improves the speech-to-speech quality and accuracy while keeping latency well within that real-time friendly 600 millisecond range. So looking further into how LLaMA-Omni2 achieves its results, this table shows the impact of training data size and type for the 7B parameter model. We see performance on tasks like spoken question answering and speech instruction following, with scores for both speech-to-text, or S2T, and speech-to-speech, or S2S interactions. Crucially, using 200,000 multi-turn dialogue samples, those back-and-forth conversations yields the best accuracy and the lowest automatic speech recognition, word error rate. This outcome really underscores the model's data efficiency and the benefit of conversational training data. Okay, let's now examine the detailed latency figures for the LLaMA-Omni2 series. This table breaks down the processing delay for different model sizes, from the 0.5 billion to the 14 billion parameter versions, and for various settings of that read/write strategy we discussed. We see latency contributions from the main large language model, the text-to-speech component, and then FM plus VOC, which refers to the causal flow matching model, and the hi-fi GAN vocoder, both key for creating the final sound. With R at 3 and W at 10, total latency for most models is impressively around or below that 600 millisecond mark, vital for smooth conversation. So, wrapping things up on LLaMA-Omni2, it is clear these models achieve impressive real-time spoken interaction. We have seen they deliver natural-sounding conversations with remarkably low delay, often under 600 milliseconds. What is particularly noteworthy is their efficiency, reaching top performance using significantly less training data than older systems. This success comes from a clever modular design, using speech-language models, AI built for spoken language, and an autoregressive streaming speech decoder, generating speech piece by piece for that smooth, real-time flow. That is all for this research roundup. Thanks for tuning in.